First of all, welcome back to today's class, day number 15 for MATH113, section 7, Applications of Mathematics in Today's World. I would like to start by going back to day number 11. Today is day number 15. If you look at day number 11, we do have something very specific that helped you accomplish the homework that has already been given to you, okay? So far, I have given you 3 weeks of homework, okay? Week number 5, week number 6, and week number 7, okay? And you will have one more set for week number 8, which will be given to you by this Friday. But when you look at the day number 11's material, which is included in lesson plan, now, most of these material has already been covered by Professor David Jerrison's coursework. Okay, in the video there, he has already covered most of this, except for the ideas on critical points and graphing of critical points, the ideas on concavity and inflection points. Now, these 2 sections we have not mentioned nor even discussed yet. Although I've already given all the materials here, particularly the videos. If you have gone through the videos on yourself, this is from the Khan's Academy, very famous video-based learning modules today. You should have no problem understanding them, and you should have no problem working out the homework exercise. Although, in the design of my lessons going through the past 3 weeks, I have shifted the focus a little bit to enhance the in-class practice, okay? To give you some problems so you can practice in class. And so we lost some time, so we cannot have done all of these as we would like to have. Now today, do you still remember what we have learned as of last week, particularly last Friday? So last Friday, we got to day number 14. And when you look at last Friday's 2 days, day number 13 and 14, you see that I have not included any specific lessons here, except that I say you can help review what you've learned from lecture 1, 2, 3, 4, 5 that we've gone through the MIT's open courseware here with the help of Professor Leonard. This is an enhanced lecture covering many of the P-calculus details you may need to understand some concept which is hidden behind the homework problems. So we did not spend time there because they're supposed to be reviews. You can use this video to review and enhance it. But we will come to these sections of the topic using David's work in this week, but not today. Today, what we are going to do is to make sure that we will go to explore the exponential functions one more time. You saw the explorations of exponential functions together with the logarithmic function last Friday. They come hand in hand, the inverse of one another. Now, before we go to see another interpretation of the exponential function from the perspective of applications of the exponential functions today, which is going to be presented to you by Professor Gilbert's-Strand, let's come back here. This is the before class activity for last week, okay? This is the before class activity for last week. And in particular, if you have missed them all, I would highly recommend that you come back and make sure you check on task number 5. Because in task number 5, I have actually included all the week's review on P-calculus mathematics for you by using the very swift latest revisions work from the calculusexpert.com. So the first week, we use that to begin our semester. This is for the second week. All those P-calculus math that you should have learned in your high school. And this is the third week, the fourth week, the fifth week, and the sixth week. And I will give you the seventh week of last week by this Friday when you were given the homework set, the last homework set for the second collections. And many of you asked me questions already, because when you work on those homework problems, they have a very interesting questions called the delta epsilon definition of something. Now this is covering your reference text, but if we go through David Jerrison's work, we've not arrived at yet. But when you come here to watch this couple of minutes per video screen here, you should have no problem understanding that. And that means what? Very much depends on your learning to learn attitude. It's already there, check on the resources and cover those holes in your revisions. The homework problems are supposed to help you to discover those holes. And these are the possibilities for you to fill up those holes. Okay? Your job is very important. Your job when you come to class is to make sure that you inspect those ideas so that you can get yourself ready for the class lectures. Today, we're here. We would like to go back to Professor Gilbert's big picture of calculus. Okay? And today we have selected one important concept, the exponential function. Now we explored the exponential function last Friday with Professor David Jerrison from MIT. Now, Gilbert Strand is another professor from MIT. Let's listen to how he introduced to us this exponential function. Okay? Let's listen and see how we can apply these functions in solving some problems. Are you ready? And then we'll go back to do some exercise. So would you please pay attention now? It is about 40 minutes time this time. Read the notes first.
Hi, well, this is Exponential Day, the day for the function that only calculus could create. Y is e to the x. And it couldn't have come from algebra, because however we approach e to the x, there's some limiting step. Something goes to zero, something goes to infinity. We've got different ways to reach e to the x, but all of them involve that limiting process, which we haven't discussed in full. Let me come back at a later time to the whole theory, discussion of limits, and just go forward here with this highly important function. And I'd like to start with its most important property, which is, so it has this remarkable property that its slope is equal to itself.
Remember that.
That's what is special about e to the x. Its slope is equal to the slope is equal to the function. Now, I have to admit that if we had a function like that, y equal e to the x, then 2e to the x would work just as well, or tan e to the x. Those would, the factor 2 or the factor 10 would be in y, and it would also be in the slope, and it would cancel, and this is a differential equation, our first differential equation. A differential equation is an equation that involves, as this one does, the function and the slope. It connects them, and that's the fantastic description of nature is by differential equations. So it's great to see this one early, and it's the most important one. When you get this one, you've got a whole lot of others solved. Okay, but I needed to give it a starting point so that the solution would be e to the x and not 10e to the x. So where shall I start it? Well, if I want it to be an e to the x, then when x is 0, e to the 0 power, some number to the 0 power, is always 1. So let me start this. Y equals 1 at x equals 0. Differential equations, you have to tell where they begin. So that's our starting point. And do you see what this means? This means that it starts at 1, and what's its slope at the starting point? The slope is also 1, so it's climbing. As it climbs, so y gets larger because it's got a positive slope. As y gets larger, the slope gets larger, so it climbs faster. And then it's gone higher, y is bigger, the slope is equal, so the slope is also bigger, so it climbs even faster. It just takes off. It climbs much faster than x to the 100th power. You might think y equal x to the 100th. That's climbing pretty well. 2 to the 100th, 10 to the 100th, but no way, it doesn't come close to keeping up with y equal e to the x. Okay, I've got several things to do, and one more thing I have to do. This is a key property, but there's another key property that is true for any 2 to the x, 3 to the x, e to the x. And that key property is also to show, I have to show this, that my function, e to the x, times e to the possibly a different x, is equal to, do you know what we want here? This has got to come out of the construction, out of this property. It's got to come, but we want this to deserve to be called some number to the x power. If we take some number x times and multiply it by that same number capital X times, then we've got that number how many times? X plus capital X. This is what? So that's a key property to be proved. So what will I do? Let me summarize in advance, outline in advance. I'm going to construct this function from its property. Then I'm going to check that it's got this property, that important equality there. Then, of course, I'll graph it, I'll figure out what E is, and I'll say something about cases where this comes up. Oh, I could even say something right away about where does this happen, that growth is equal or proportional to the function itself. It happens with interest, with money in a bank. When you get interest, the interest is proportional, of course, to the amount there. And if they add that interest in, if you don't take it out and spend it, but you compound it, put it in there, then you have more money. When they compute the interest again, it's computed on that larger amount and is more interest than the first time. And so it goes. So that's, money in a bank is a case, it's a case of exponential growth. I mean, a hedge fund grows faster than our bank account does, but all following e to the x. If you just hang on long enough, you're way up there. Okay, so here's my job. Follow this rule and start at y equal 1. So can I just do it this way? Here is my function y of x that I want to construct. I want to build that function, and I know that it starts at 1, but it's going to have some more things. Now, this has to equal dy dx. These have to be the same. That's my rule. So dy dx is going to start with a 1. But now I can't stop, because if the derivative is a 1, I have to put an x up here so that its derivative will be 1, right? Its slope will be 1. That's the steadily climbing x whose slope is 1. But now these are supposed to be equal again. So I have to put this x also here. But now I've got to add something more on the top, so that the slope will be 1 plus x.
You see, it's a very interesting
reason. The x was 1. What do I need here to give the slope to be x? Remember, x squared had the slope 2x, so I need half of x squared so that I'll have 1x. So I need a half of x squared. Good. The slope of that is this. But I'm also trying to get the two to be equal. So I have no choice. I have to put in the 1/2 x squared there. You see, I'm never going to catch up.
Right.
Or only if I go forever. That's the point. I'll have to go forever. And what will the next one be? Oh yeah. If you see the next one, then we can see the pattern. So it's going to be, now what am I doing? This one has to have this slope. I'm trying to I'm fixing the top line now. If I'm aiming for a slope of x squared, then I need some number of x cubes. So how many x cubes do I need?
1/6.
Well, I need to know what's the slope of x cubed. The rule for powers of x to the n, is n times one smaller power. The slope of x cubed is 3 times x squared. So I better divide by that 3. So that the 3 cancels the 3. Now the slope of that, the 3x squared, the 3's would cancel and I get x squared. But I'm looking for 1/2 x squared. I need also a 2. You see that it's 1/6 of x cubed that's going to do the job. 1/6 of x cubed. Because the slope, the 3 cancels the 3, and I wanted to end up with a 2. And now, you know what's coming? These are supposed to be equal. I have to have this 1/6 x cubed down here too. And I never get to stop. Can you see, we have to see, okay, what is a typical, after I've done this, say, n times, I'd like to have some idea, what is it when I get up to x to some nth power, then it's multiplied by some fraction, and I'm looking to see what is that fraction. What is that fraction? And then, of course, they'll all show up down there again. Well, if you see this pattern, this was 3 times 2. You could say 3 times 2 times 1. This one was 2 times 1. This one was just 1. It's n factorial. N factorial is what I need. I need n times n minus 1. I need all these numbers all the way, and I'll throw in the 1 at the end. And I have to put the mathematicians' take it away symbol, the little 3 dots that mean don't stop, keep going. But do you see that this will be okay? This is called n factorial, x to the nth over n factorial, because when I take the slope of x to the nth, an n will come down, cancel that n, x, I'll have it 1 lower power. You see, when I take the slope of this, I'll have the n will cancel the n, so I'll still have these other guys down below, and I'll have x to the n minus 1, and that will be x to the n minus 1 over n minus 1 factorial, that will be the previous one. But now I have to add in the x to the nth over n factorial, because top, because y and dy dx have to be the same, so I have to keep going. Okay, so you might say, well, you're going to blow up. Not personally, the series. But what saves you is the fact that these n factorials, those fractions, the n factorial gets to be really large, really fast. Faster than this x to the nth could grow. So altogether, these terms, x to the nth over n factorial, they get extremely, extremely small. And then this series of things comes, it comes to a limit. It doesn't keep going, getting bigger and bigger and bigger as I add more terms, because what I'm adding is so small, so small. And that's the point where we have to discuss limits later. Okay, so that's my construction. Construction complete. The function y to the exponential function, e to the x, this is e to the x, is being defined by 1 plus x plus a half x squared plus a 6x cubed, and so on. Okay. I've got a function. Now, its property. And the key property is this one. Can I move to the next board? So the next step is check. Well, I've asked you. I've got e to the x. And let me write again what it is. 1 plus x plus a half x squared plus 6x cubed, and so on. And then I've got e to any other power, or even the same power. 1 plus, I'll just use capital X for this power. 1/6 of capital X cubed plus so on. And I want to multiply those and see what I get. Okay, I apologize. Here I ask you to believe in this infinite series, and a little dodgy, but it works. And now I ask you to multiply two of the things. You may say, okay, you're asking a lot here, but go, just hang on. Let's multiply these. E to the x times e to the capital X. Because that's what I'm interested in knowing. Okay, can you just do all the multiplications? So, and we'll see what we get. Okay, so 1 times 1 is 1, no problem. 1 times x is the x. 1 times this x is the big X. Now, can I keep going? All right. Well, 1 times a half x squared is, and now I have a x times a big X. And now I have a 1 times a half big X squared. And more, of course. Notice the way I'm doing it is like I'm keeping all the things that have 2 x's together. And then I would keep all the things that have 3 x's together, and so on. Now, what is it that I'm hoping? I'm hoping that this is the same as the series for x plus capital X. Okay, what's that? That's my exponential series, and every time I have to put in x plus capital X. In other words, of course, it starts with 1, then it has the x plus capital X, and then it has the 1/2 of x plus capital X squared, and it keeps going. And I just want you to say yes. I guess I hope you say yes. when I ask, is this big multiplication the same as this one? Well, I think it is. Let's start the check anyway. The ones are good. The x and the x. I'm really just putting parentheses around now I'm going to put parentheses around all the second degree terms and say, is that the same as that? Yeah, this is the critical point here. Do we at least start out correctly? So you have to remember how do you do, but of course you do remember how to multiply x plus capital X by itself. You just do the multiplications. X, when I multiply that by itself, I get x squared with a half, I get that. And then you remember, how many x times x's do I get? Little x times big X, there would be 2 of those. But then the 1/2 factor leaves me with 1, and that's what I want. And then finally, this guy by himself, squared, is the 1/2 capital X squared that I also want. So far, so good. Do you want to see the cube terms? I don't, well, I'd rather you did it, but I should at least show that I'm willing to try. So what do I mean by the cube terms? I mean that here I want to get the next one should be 1/6 of x plus x cubed. And from the multiplication, I get some separate pieces. I get 1 times this, I get a 6. When I do that multiplication, I get 1/6 x cubed. And then I maybe get some 1/2 x squared times x. Oh, you see why I would rather you did this. But I'll finish this little line. There's also a 1/2, an x times 1/2 x squared, so that's a half of x times the big X squared. And then there is the 1 times the 1/6 x cubed. So those are the 4 pieces that come, 3rd degree, when I do the big multiplication, and they have to match the 3rd degree term in the last line. And they do match. If we cube thing, do you remember the great words to say now? Binomial theorem. The binomial theorem tells you how to take the nth power of a sum, like x plus capital X, to the nth power. It tells you all the many pieces you get, and those many pieces are exactly the pieces that we get directly by multiplying that line by that line. So the binomial theorem at long last pays off and confirms our great property here. So this is a big deal. Okay. So let me now come back here, having checked that. I wanted to say something about this series. 1 plus x plus a half x squared, where the typical term is x to the nth over n factorial. This is the, I would say, the second most important infinite series in mathematics, the exponential series. And it's the way I wanted to construct e to the x by matching term by term and seeing that these n factorials show up. You might want to know, what's the most important series? Reasonable question. For me, the most important series would be the one looking like this, except it doesn't have the fractions. For me, the most important series would be the one, I'll slip it up here, 1 plus x squared without the half, plus x cubed without the 1/6, plus so on, plus x to the n without this n factorial that's making it so small. Can you see this? 1 plus x squared plus x cubed plus x to the n? That, I think it's called the geometric series, powers of x. Now, it's simpler because it doesn't have these fractions. But it's riskier because those fractions were making the exponential series succeed. Whereas here, with the geometric series, well, look what happens when x is 1. When x is 1, we have 1 plus 1 plus 1 plus 1 plus 1, forever all ones, it blows up. And when x is bigger than 1, that series blows up even faster. So this series, the geometric series, this most important one, does succeed, but only for x, only when x is below 1. X equal 1 is the cutoff, and it fails after that. There is no cutoff for that exponential series because of these dividing by these bigger and bigger numbers. This works for all of us. Okay, so those are the two series. Okay. Now, what happens, so let me ask you, what happens if I put x equal 1 in the exponential series? That gives me e to the first power, which is e. So finally, you may say, this is rather late in the day, I'm going to figure out what e is from this series. Put in, set x equal 1, and you learn that e to the first power, which is e, is, can I just put it in? 1 plus, x is 1 plus 1/2 of 1 squared plus 1/6 of 1 cubed. What's the next term in this? So these are numbers now, and I'm getting a number. I'm getting this incredible number e, named after Euler. Euler was a fantastic mathematician. I think he wrote more important papers than any mathematician in history. So he was allowed to name this number after himself. E. E-U-L-E-R, his name is spelled. Okay, what's the next term? This is 3 factorial, right? 3 times 2 times 1. The next term will be 4 factorial. I'll multiply that by 4. It'll be a 24th. And then times 5, 120th. And so on. They're getting small. What can I tell you about this number? It will be a definite number. It's more than, well, it's certainly more than 2.5, because I start with 2.5 here, and then I add these. Well, I could even throw in 1/6. That's more than 2 2/3, would that be? If I quit here, I'd have 2 2/3, and then I get a little more. It's easy to show. No way you would reach as far as 3. These later terms are dropping too fast. And actually, the number turns out to be, so it's 2 point something, 2 point, let's see, a little more than 2 2/3. So it's around 2.7. But it's not exactly 2.7. In fact, it's not exactly any fraction or any finite decimal. It goes on and on. 1, 8, 2, 8, something. I think there are like more 8s than you'd expect right here at the beginning, but then in the long run, not. In the long run, yeah, so that's the number e. Okay. Oh, so now we know e. We know e to the x, we know e, we know this thing. I should draw a graph, right? That's the other thing you do with a function, is draw a graph. Okay, so here's a graph. This is x. Let me put in x equals 0 here and x equals 1 here. And this is going to be a graph of e to the x. And at x equals 0, what is it? We started with that. It should be, so this is y, I'm graphing y, and it starts at 1. That's what we said. At x equals 0, I've started at 1 with a slope of 1. So I have a slope of 1, but the slope is climbing up, and it reaches here. That height is what? E. That height is E. So, because when we said x equal 1 here, we got E. So it's climbing, 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 and now what about on the other side? That had a slope of 1, so it was more like that. Now what about when x is negative? When x is negative, this is a highly useful fact. Suppose, well, I want to think about e to the minus x. Well, now let me just take capital X to be minus little x. So I get e to the x times e to the minus x. What is that? What does that equal? If I multiply e to the x times e to the minus x, as usual, I'm supposed to add these. I get 0, so I get e to the 0, which is 1. In other words, e to the minus x is 1 over e to the x, which we fully expected, so that at x equal minus 1 here, I'm down to 1 over e, 1/3 approximately. So it's going down. This is, in this way, it's decaying very fast. It almost touches that line, but never quite. This way, it's climbing. It's growing really. Well, it's growing exponentially. And that's what its graph looks like. And now I would like to connect back at the end of this lecture to the insurance business, to the interest business, the bank compounding interest. Can I take your time with that important example of the exponential function? And we'll see a new way to reach e. I like this way. I like the way we did it with the infinite series. But here's another way. So, suppose you're getting 100% interest. Generous bank. Okay. So then, and you start with $1 at 100% now. It's the 100%. And the bank gives you interest at the end of every year. So at the end of the first year, you had $1 in the bank. It adds in 100%, it adds in another $1. So now you've got $2 in the bank after the first year. At the end of the second year, it gives you 100% of what you've got in the bank, so it gives you 2 more, it gives you 4. At the end of the third year, it gives you an additional 4, you're up to 8, and you see what's happening. It's the powers of 2. Well, that's pretty good growth. But it's not calculus. Calculus doesn't do things in steps of a year. Calculus says, cut that step down. I mean, you would want to ask your bank, couldn't you just, figure the interest a little more often? And put it in there, figure it every month? So what would happen if you figured the interest every month? Of course, you wouldn't get 100% interest in a month. You'd get 100% divided by 12. Because we're only talking about 1 month. So if it was months, you start with 1. You have 1 plus 1/12. That's what you'd have after a month. Now, what would you have after 2 months? And what would you have after 12 months? Well, we're going to follow the rule. This is what they gave you the 1/12 at the end of January. So through all of February, you've got 1 plus 1/12 in there. At the end of February, they take 1/12 of that, add it in. What you get the next time is 1 plus 1/12 squared. That's what you have when they, essentially every time, they're going to multiply what you've got by this number 1 plus a 12th. 1 to give you, leave the money in. You have to leave your money in, I'm sorry. Plus a 12th of it for the interest. And then twice, and after 1 year, it's done this. You see what happens after 1 year? It's multiplied 12 times. 1 plus 1/12 to the 12th power. And that's better than 2, right? You got the 2 only when they put the interest in just once a year. Now we're speeding up the bank and getting more out of it. So I don't know exactly what 1 plus 1/12 to the 12th power is, but I know it's more than 2. And actually, I'm sure it's not more than 3. In fact, I'm claiming that it's not as much as E, 2.7. So, but it was worth doing to get them to compound every month. But of course, you think, okay, I'm on to a good thing every day. Why not? So what would every day be? 1 plus 1 365th. That's the interest you would get for just that day, but then they would compound it 365 times. So that would be a little more than this, because they're adding the interest in more frequently. And in general, I'm going to divide the year up into n pieces. In every piece, they multiply my wealth by 1 plus 1 over n, and they do it n times in a year. And the beautiful thing is that as n goes to infinity, and calculus comes in because we're asking them to compound interest continuously, not just every month, not every day, but not every second even, but all the time. You don't get an infinite amount out of this. You get E. That approaches, as n gets bigger, that approaches this number E. That's another way to construct E. As the limit, you see this is like, as n gets bigger, it's like 1 to the infinity, which is kind of meaningless. I don't want to say that 1 to the infinity. I had an email the other day that said, well, 1 to the infinity is E. What's happening? That's not true. It's this thing that's going to 1, this thing that's going to infinity, then the combination goes to E. Okay. So that's the application that shows the number E appearing again. Okay. You've got the essence of e to the x. I just would like to say one thing coming back to the very beginning here. The great differential equation dy dx equal y. That was beautiful, which we've now solved. Now, I want to ask, what if the differential equation was dy dx is some multiple of y? How would that come out? Well, up to now, C was 1. We were getting 100% interest per year. But now, if C is sort of the interest rate, the growth rate, or the decay rate, if C is negative, we may be losing money in this bank. So, can I just tell you what is the solution to this differential equation? When I tell you, and we learn about taking derivatives, you'll see, of course, that's all it is. It's just the solution to this one. Also, I'll also start at 1, the solution to that one is y of x is e is coming in again, to the cx. What I'm doing is like changing the rate of, I've made the rate of change c. And then that c is going to come up there, and in the derivative, the slope of this guy, that c will come down. The slope of this will be c e to the cx, which is cy, which is what that second differential equation tells us. So that's just a comment looking ahead. That we've solved not only the most important differential equation with the most important function that calculus creates, but a whole collection of related equations in which the rate can be any fixed number. C. Okay, thank you.
This has been a production of MIT OpenCourseware and Gilbert Strang. Funding for this video was provided by the Lord Foundation. To help OCW continue to provide free and open access to MIT courses,
it's a very interesting introduction of the exponential functions, and this time, instead of approaching the exponential functions with a unique purpose of telling you how to differentiate functions, you see a little bit more interesting about the compositions of the function. And indeed, Professor Strang here had introduced to us to two important series, the exponential series and the geometric series, and their connections with the way the compound interest is being done. Now, we have given you a very interesting, what we call the treatment of these functions. Now, I would like you to pay attention to the notes given of last time. That is from Professor David Jerrison's. Okay, let me enlarge these notes, okay, so we can see it much more clearly. I would like you to spend time to follow these notes at this point. I'm going to give you at least minutes to go through systematically, step by steps. I'm going to extend this to you. I would like each one of you to read the notes now to refresh your memory on the exponential functions. Last time, the focus is on taking the derivatives of the exponentials and not the terms. It's telling you how can you differentiate a function if it is an exponential function, if it's a logarithmic function. And this time is different. Remember, last time, Professor David Jerrison started up with this set of properties that we can use directly. But this time, when you look at the video presented by Professor Gilbert Strang, he's actually telling you how this is possible. Okay, how this is possible. So it's very interesting to look at two different approaches in learning calculus when it comes to the exponential functions. So today's main task, as of last time, done by Professor David Jerrison, is we're going to find this exponential function, starting from the principle, the first principle, which is the slope. Okay, the slope as delta x approaches 0. How are we going to write the expressions? And then he extend from this and factor this out and say that a to the power x could be factored out under the very important assumptions of y. Because here x could be considered as a constant as delta x approaches 0. And then he introduced this particular m guys here to represent this important expressions, and he called this the slope. Now we do not yet know what this is, but we can say this by plugging this in. Alright? So every time when you listen to a presentation of this very well-established concept, when we approach it from different angles, but listening to different lecture, you have different approaches. And so here is very interesting. He said, let's try to describe A using two methods. One is the analytic method, The other is the geometric method. Okay. Do you remember what's the differences between the analytic method and the geometric method? Okay. The geometric method is on the slope of something. The analytic method is on interpretations, the instantaneous change. Okay, the two essential concepts on the specific branch of calculus called differential calculus. So at this point, you can see that at x is equal to 0, this guy here, okay, approaches to this, because we have the expressions as you can see above. What this means is, when you come down to this, which is equivalent to the geometric definitions of MA, the slope. MA is the slope of the graph y equal to a to the power x at x equal to 0. Okay? So what does it mean? At x is equal to 0, for this particular guy here, what's the values of this? What's the values of this? David said, we're going to find a magic number so that the magic number, when we plug in, we got 1. Oh, excuse me. I thought I'm okay today. So, look at the trick. The trick to figuring out what this is to back the questions and define E as the number such that this particular value is equal to 1. So we are holding up to this particular assumptions to find the values of the derivative. So hopefully, hopefully you have already gone through the revision notes. It's very important after watching or listening to a lecture, you refer to the notes to check the concept. And I hope that you develop this habit of learning at the end of each hour lecture, because that is very important for you to understand the meaning of this. And in today's lecture, given by Professor Gilbert-Strand, he used a very different way to help us to understand this. Instead of helping us to come to this particular expression, he started out by telling us this is the property we want. The slope of a function, which is the derivative of the function, is exactly equal to the function itself. He's using the exponential function as an example. In other words, today's lecture is a very interesting continuation of last Friday's lecture by starting from this point onward to tell us expressions of this e to the power x in terms of the specific terms, just like in the specific equations, we call it a polynomial. But Professor Gilbert-Strand did not need us to understand the inverse functions of this exponential function, which is the natural log. But we learned this last week, okay? So I hope that with that particular context given to you, you understand the importance of the learning. Now, the question is, how are we going to apply those concepts we learned in the particular case here is to an exponential function? I have prepared something else for you, but I'm going to give it to you on Friday. Instead, today, I want you to listen to the continuations of this lecture from Professor David Jerson for another 10 to 20 minutes. Okay? And that is lecture number 7.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Right now, we're finishing up with this first unit, and I'd like to continue in this lecture, lecture 7, with some final remarks about exponents. So what I'd like to do is just review something that I did quickly last time and make a few philosophical remarks about it. I think that the steps involved were maybe a little tricky, and so I'd like to go through it one more time. Remember that we were talking about this number ak, which is 1 plus 1 over k to the kth power.
Right.
And what we showed was that the limit as k goes to infinity of ak was e. So the first thing that I'd like to do is just explain the proof a little bit more clearly than I did last time, with a little bit less, fewer symbols, or at least with this abbreviation of the symbol here to show you what it was that we actually did. So I'll just remind you what we did last time. And the first observation was to check, rather than the limit of this function, to take the log first. And this is typically what's done when you have an exponential, when you have an exponent. And what we found was that the limit here was 1 as k goes to infinity. Now, so last time this is what we did. And I just wanted to be careful and show you exactly what the next step is. If you exponentiate this fact, you take e to this power, that's going to tend to e to the first power, which is just e. All right? And then we just observe that this is the same as ak. All right, so the basic ingredient here is that e to the log a is equal to a. That's because the log function is the inverse of the exponential function. Yes, question?
0, because it's k multiplied by ln of 1 plus 1 over k. As k goes to infinity, that's ln of 1, right? Which is 0.
So the question was, wouldn't the log of this be 0 because ak is tending to 1? But ak isn't. You said it was. K times, if you take the logarithm, which is what we did last time, logarithm of ak is indeed k times the log of 1 plus 1 over k. That does not tend to 0. This part of it tends to 0, and this part tends to infinity. And they balance each other, 0 times infinity. And so we don't really know yet from this expression. In fact, we did some cleverness with limits and derivatives to figure out this limit, and it was a very subtle thing. It turned out to be 1. All right? Now, the thing that I'd like to say, I'm sorry, I'm gonna erase this aside here, but you need to go back to your notes and remember that this is what we did last time, because I want to have room for the next comment that I want to make on this little blackboard here. What we just derived is this property here, but then I made a claim yesterday, and I just want to emphasize it again so you realize what it is that we're doing. I just reversed I looked at this backwards. One way you can think of this is we're evaluating this limit and getting an answer. But all equalities can be read both directions. And we can write it the other way. E equals the limit as k goes to infinity of this expression here. So that's just the same thing. And if we read it backwards, what we're saying is that this limit is a formula for e. So this is very typical of mathematics. You want to always reverse your perspective all the time. Equations work both ways. And in this case, we have two different things here. This e was what we defined as the base, which when you graph e to the x, you get slope 1 at 0. And then it turns out to be equal to this limit, which we can calculate numerically. If you do this on your calculators, you of course will have a way of programming in this number and evaluating it for each k. And you'll have another button available to evaluate this one. So another way of saying it is that there's a relationship between these two things. And all of calculus is a matter of getting these relationships. So we can look at these things in several different ways. And indeed, that's what we're going to be doing, at least at the end of today, talking about derivatives. A lot of times when we talk about derivatives, we're trying to look at them from several perspectives at once. Okay, so I have to keep on going with exponents because I have one loose end. One loose end that I did not cover yet. there's one very important formula that's left. And it's the derivative of the powers. We actually didn't do this. Well, we did it for rational numbers r. So this is the formula here. But now, sorry, let's just stick this in here. This is we're going to check this for all real numbers r, so including all the irrational ones as well. This is also good practice for using base e and using logarithmic differentiation. So let me do this by our two methods that we can use to handle exponential type problems. So method one was base e. So if I just rewrite this base e, again, that's this formula over here. X to the r is equal to e to the log x to the power r.
Looks very interesting.
Which is e to the r log x. Okay, so now I can differentiate this. So I get that d by dx, x to the r. Now I'm gonna use prime notation because I don't want to keep on writing that d by dx. E to the r log x prime. And now what I can do is I can use the chain rule. Right? The chain rule says that it's the derivative of this times the derivative of the function. So the derivative of the exponential is just itself. And the derivative of this guy here, well, I'll write it out once. It's r log x prime. So what's that equal to? Well, e to the r log x is just x to the r. And this derivative here is, well, the derivative of r is 0, right? This is a constant factor, it just factors out. And log x now has derivative, what's the derivative of log x? 1 over x. So this is going to be times r over x. And now we rewrite it in the customary form, which is r, we put the r in front, x to the r minus 1. Okay? So this is the just derived form. And it didn't now matter whether r was rational or irrational. It's the same proof. Okay, so now I have to show you how method 2 works as well. So let's do method 2, which we call logarithmic differentiation. And so here I'll use a symbol, say u for x to the r, and then I'll take its logarithm. That's r log x. And now I differentiate it. I'll leave that in the middle because I want to remember the key property of logarithmic differentiation. But first I'll differentiate it. Later on, what I'm going to use is that this is the same as u prime over u. This is one way of evaluating the logarithmic derivative. And then the other is to differentiate the explicit function that we have over here. And that is just, as we said, r over x. So now I multiply through, and I get u prime is equal to u times r divided by x, which is just x to the r over x, which is just what we did before. It's r x to the r minus 1. Again, you can now see by comparing these two pieces of arithmetic that they're basically the same. Pretty much every time you convert to base c or you do logarithmic differentiation, you will amount to the same thing, provided you don't get mixed up. You generally have to introduce a new symbol here. On the other hand, you're dealing with exponents there. It's worth it to know both points of view. All right.
We're going to stop here for this lecture to make sure that you understand this very important part, which is not discussed last time. And of course, when you go home, please finish watching and learning from the remaining 40 minutes. Let me take attendance first, and then we'll come back with a couple of comments to get you ready for this Friday's lecture. Okay? So, Waikiki, Johnson, thank you. Alex, not here today. Stella, thank you. Viviana, thank you. Jordan, thank you. Star, thank you. Chaos, thank you. Lovia, thank you. Louise, thank you. David is not here today. Chen, thank you. Viola, not here today. Okay. Oh, thank you. Sorry. Candy, thank you. And then Mei-Ling, thank you. Iris, thank you. Bella, thank you. Cindy, thank you. Vivian, thank you. Patrick, thank you. Jeanette, thank you. Ivy, thank you. Celia, thank you. And then Michelle, thank you. Lizzie, thank you. Another page. Doris, thank you. Calvin, thank you. Jeremy, thank you. Andy, thank you very much. And so, this Friday, when you come back, you're going to learn not the continuations of the lecture you saw. This is the remaining things that you believe you can handle yourself. Instead, we will come back to learn something about curve sketching, maximum, minimum. These are parts that I mentioned at the very beginning, should have given to you on day number 11. Okay? So I'll see you back on Friday. And make sure to check out the latest set of homework release for week number 7. I will release the last set this Friday for week number 8. Okay? You need a group discussions on those homework. Share the burden. Okay? It's very important. And your midterm exam, November, I think it's after October 25th. Okay? I told you it's already on November 1st, right? Not November 1st. Let's double check. After this day, October 25th, it's on the 30th. Yes, October the 30th, not November. October the 30th, Friday. Okay? I will keep that in the teacher's message. Okay, see you on Friday. If you have a need to check the answers of the homework exercise before I release the answer, come to my office during office hours. Monday from 5 to 6:30, Wednesday from 12 to 1:30. Okay? Thank you very much.